There's something almost hypnotic about watching raw steel get bent to human will. And when we're talking about a plate that's 120 millimeters thick, 3,000 millimeters wide, and rolled into a cylinder with a finished diameter of 1,400 millimeters, you're not watching a craft anymore. You're watching engineering at a scale most people never get to see up close. The Faccin 4-roll plate rolling machine is a beast in the most respectful sense of the word. Unlike a standard 3-roll machine, the 4-roll design gives operators something critical: the ability to pre-bend both ends of the plate in a single setup without having to flip or reposition the material. That matters enormously when you're working with steel this thick. Every repositioning is a risk, a time cost, and a source of potential misalignment. Here's how the process unfolds. The steel plate, already cut to precise dimensions, is fed into the machine and gripped between the rollers. The top roll applies downward pressure while the two side rolls adjust to control the curvature radius. The bottom roll serves as the driving force, pulling the plate through with consistent, controlled speed. As the plate passes through multiple times, the radius tightens progressively. You don't smash steel into shape, you convince it to bend, pass by pass, with patience and precision. What makes this particular job remarkable is the sheer wall thickness. At 120 millimeters, this isn't sheet metal work. It's closer to forging territory. The machine has to apply enormous even force across the entire 3,000 millimeter width simultaneously, or you risk a plate that's slightly more curved on one side than the other. That's a reject. At this scale, a reject costs tens of thousands of dollars and weeks of time. Once the plate reaches the target curvature, the two ends are brought together and tack welded to hold the cylinder shape. Then it goes to the welding station for full seam welding, often a multi-pass submerged arc weld for penetration and strength. The finished ring will eventually become part of a pressure vessel or structural shell designed to handle serious industrial loads. Next, aluminum is everywhere, and we mean everywhere. Your car's engine block, the window frame you're leaning against, the heat sink inside your computer, the frame of your smartphone. But here's something most people never think about. Almost all of that aluminum started its life as a round billet that got squeezed through a die at high temperature and enormous pressure. That process has a name: extrusion. And when it's done at industrial scale, it's one of the most fascinating manufacturing sequences you'll ever watch. Here's how the extrusion process works, step by step. It starts with the billet, a solid cylindrical slug of aluminum alloy, typically 6-inch or 7-inch diameter for medium-duty extrusion presses. The alloy grade depends on the application. 6061 and 6063 are the most common structural alloys. 6063 in particular is the go-to for architectural profiles like window frames and door thresholds because of its excellent surface finish after anodizing. Before the billet goes anywhere near the press, it has to be heated. And this is where MM Metacraft's internal hot melting furnace setup becomes relevant. Rather than sourcing pre-cast billets from an outside supplier, a vertically integrated operation melts its own aluminum and casts its own billets on site. The billets are heated in a log furnace to the extrusion temperature, typically between 750 degrees Fahrenheit and 950 degree, 400 to 510 degrees Celsius for 6x6 series alloys. The exact temperature profile matters. Too cold and the press force spikes, risking die damage. Too hot and the metal loses structural integrity, leading to surface defects and profile distortion. The furnace heats the billet with a temperature gradient, slightly hotter at the back end, to compensate for the cooling that happens as the leading edge of the billet contacts the cooler press components. Once the billet is at temperature, a loader transfers it into the press container. The ram advances and begins compressing the billet. The aluminum, behaving almost like a very stiff fluid under this kind of pressure, has only one place to go: through the die opening. The die is a precisely machined tool steel disc with an aperture shaped exactly like the cross-section of the finished profile. As the aluminum flows through, it takes that shape and exits the press as a continuous strand: your window frame, your heatsink, your structural channel. On a 1,100-ton press, the ram force is enough to push material through complex multi-void dies. Think hollow profiles with internal channels, like the kind used in automotive structural components or industrial heat exchangers. The 600-ton press handles lighter profiles and smaller cross-sections, maximizing throughput on high-volume architectural runs. As the profile exits the die, it's carried along a run-out table, a long roller-supported surface that extends 80 to 120 feet from the press face. The profile is still hot and somewhat malleable at this point. At the end of the run-out table, it's quenched, cooled rapidly with air or water spray to lock in the metallurgical properties established during extrusion. Speed matters here. The time between die exit and quench affects the final temper of the alloy and its mechanical strength. After quenching, the long strands are cut to standard mill lengths, typically 20 to 25 feet, and moved to the stretcher. The stretcher grips both ends of the profile and applies controlled tension, pulling it straight and relieving residual stresses that built up during extrusion. This step is what gives extruded aluminum its characteristic flatness and dimensional stability. From the stretcher, the profiles go to the aging oven, where a controlled heat treatment cycle, typically around 350 degrees Fahrenheit for several hours, develops the final temper designation, usually T5 or T6, depending on the alloy and application. This artificial aging step is what pushes the tensile strength from around 15,000 psi in the freshly extruded state up to 38,000 psi or higher, strong enough for structural applications that engineers actually depend on. The finished profiles are then cut to customer-specified lengths, inspected, and packed for shipment. For architectural profiles destined for anodizing or powder coating, surface quality is inspected closely at every stage, because a scratch that develops during extrusion shows up clearly after anodizing, and there's no hiding it. There's a certain kind of project that separates the serious steel fabricators from everyone else. And a custom-engineered warehouse spanning 300 meters with 70-meter clear spans is exactly that kind of project. This is the work Jensen Steel Fabricators was built for. The beams in this project aren't off-the-shelf rolled sections. They're custom-fabricated welded beams, also called built-up beams or plate girders, where the web and flanges are cut from plate and welded together to precise dimensions. Why go custom? Because at a 70-meter span, the bending moments involved are enormous, and standard hot-rolled sections simply don't come in the depth or flange size required to handle those loads efficiently. By building the beam from plate, Jensen's engineers can optimize the cross-section, deeper web for flexural stiffness, wider or thicker flanges where the bending stress is highest. The fabrication process begins with the steel plate arriving in the yard, high-strength structural steel, likely grade 350 or above, selected for its yield strength and weldability. Plates are cut to the web and flange dimensions using CNC plasma or oxy-fuel cutting. then cleaned and prepped for welding. Assembly starts by tacking the flanges to the web, holding geometry while the fit-up is verified. Then the longitudinal fillet welds, typically dual-sided, are laid in using submerged arc welding, SOKOYO. SAW is the preferred process for this application because it deposits weld metal at high rates with deep penetration and excellent quality, all under a layer of flux that shields the arc and produces a clean, consistent bead profile. For beams of this size, that weld has to perform for the life of the structure, potentially 50 to 100 years. After welding, the beams are checked for camber, a deliberate upward pre-bow built into the beam during fabrication to compensate for dead load deflection. When the beam is loaded by the roof structure and its own weight, that camber is designed to flatten out, leaving a level chord. Getting the camber right is as much art as science for a beam this long. Drive down any American street after dark and you're surrounded by them. Street light poles, standing silent and steady, holding up the lights that keep neighborhoods safe, intersections visible, and highways passable. They're so ordinary that most people never give them a second thought. But behind every one of those poles is a manufacturing process that's more precise, more automated, and more sophisticated than you'd ever guess from the outside. SOKOYO is a Chinese manufacturer that's built a strong reputation in the global outdoor lighting market, not just for the lights themselves, but for the complete pole and luminaire systems that go with them. The raw material for streetlight poles is typically hot-rolled steel coil or sheet, usually 2 to 5 millimeters thick, depending on the pole height and wind load requirements. Taller poles for highway or arterial road applications use heavier gauge material. Residential streetlights can get by with lighter stock. The process starts at the cutting and blanking station. Incoming steel sheets are fed through a CNC shearing line, where they're cut to precise blank dimensions. The blank profile for a tapered octagonal pole, the most common style in modern street lighting, is a parallelogram-like shape with angled edges that, when formed and closed, create the tapered polygon cross-section. From the cutting station, the blanks move to the press brake forming line. SOKOYO uses heavy-duty CNC press brakes with long bending tables, similar in concept to the Accurl machines we saw in clip 2, to form the flat blank into the multifaceted tapered shape. For an octagonal pole, this requires a specific sequence of bends, typically starting from the center of the blank and working outward to prevent the material from buckling or shifting during forming. Once all the bending passes are complete, the pole blank is closed. The two longitudinal edges are brought together, forming the continuous seam that runs the full length of the pole. This seam is the structural backbone of the assembly, and welding it correctly is critical. SOKOYO's production line uses automated MIG or MAG welding systems for this seam weld. The torch travels along the full length of the pole at controlled speed and heat input, laying down a consistent, full penetration weld. The automated setup eliminates the variation that comes with hand welding on a long seam, and it's dramatically faster than manual methods on a production scale. After seam welding, the pole goes through a straightening process. Welding introduces heat into one side of the structure, which causes residual stress and a slight bow in the finished assembly. Straightening, using hydraulic or mechanical correction, brings the pole back into alignment within specified tolerances. For a 10-meter pole, the typical straightness specification is within 1/1000 of the pole length, meaning no more than 10 millimeters of deviation over the full height. That's a tight number for a long, relatively slender steel structure. The next major station is the base plate and top cap assembly. The base plate, a heavy steel disc with bolt holes for anchor bolt attachment, is positioned and welded to the bottom of the pole shaft. This weld is a full circumference fillet or groove weld, applied with enough passes to develop full strength. The top cap, which closes the open end of the pole and provides a weather-tight terminus, is welded on in similar fashion. Access doors, small rectangular openings in the lower section of the shaft for electrical connections, are also cut and framed at this stage. From fabrication, the poles move to surface treatment, and this is where longevity is really determined. The standard process for road-grade streetlight poles is hot-dip galvanizing. The entire pole assembly is immersed in a bath of molten zinc at around 840 degrees Fahrenheit, 450 degrees Celsius. The zinc reacts metallurgically with the steel surface, forming a series of iron-zinc alloy layers, topped by a pure zinc outer coating. This galvanized coating is sacrificial. It corrodes preferentially to protect the underlying steel. And when properly applied, it provides corrosion protection for 50 years or more in typical outdoor environments. For poles intended for decorative or architectural applications, think downtown streetscaping or park lighting, the galvanized surface is then powder coated. It's a long way from a coil of flat steel to a finished streetlight pole standing 40 feet tall at a city intersection. But processes like SOKOYO's are what make it possible to build and light cities at scale, reliably, affordably, and with a quality that's designed to last long enough that most of us will never have to think about where that light above us actually came from.